All right. This video is mostly for students who were not present on August 26th because we went through uh, test review questions. So I just want to make this quick video so you'll be able to catch up with what we did. So the first question we went over is the force due to gravity on a body is the body's what? So if you check your notes, you realize that it is the body's weight. Then the second question, when the mass of an object is compared to its volume, the concept is called density. Okay. When you compare the mass of an object to its volume, that is density. So when we say 1 kilogram of iron and 1 kilogram of cotton, which one weighs more than the other one, or which one has more mass? The answer is they all have the same mass. But if you compare the mass of the iron to its volume and the mass of the cotton to its volume, you realize that the cotton occupies more volume than the iron. That's why the iron is more dense than cotton. When we say 1 kilogram weighs 10 Newton, we mean that 1 kilogram is 10 Newton is true at Earth's surface, is true everywhere. Mass and weight are one and the same thing. So if you check what we did last week, you will realize that the gravitational pull on the Earth is different from the gravitational pull on different planets. That's why you see someone is able to walk normally on Earth, but when they go to space, they start floating like you saw the astronaut that landed in space. It is because the gravitational pull on the Earth is way different or way larger than the gravitational pull in space. And every object on the Earth's surface is accelerated at a value of 10 meters per second square. That is constant and that is true for the Earth and the Earth only. It is not true for any other place outside the Earth. And so that is why this answer is B. It's true at the Earth's surface. Because if you multiply 10 kilogram by 10 meters per second square, that is what is going to give you 10 Newton. And that only applies to the Earth's surface. The mass of 1 kilogram of iron, again, remember, mass does not change. The only thing that changes is the weight. The weight on the moon for a 1 kilogram object will be different from its weight on Earth, but the mass is the same on the moon. Mass does not change. Remember, mass is the amount of matter that we have in an object. It doesn't change irrespective of where the object is. Now, this is a question on resolution of forces or calculating net force that's acting on an object. If you have a pair of 3 Newton and a pair of 4 Newton, the question is, if you arrange these forces, which of them cannot be a resultant? A resultant, remember, is another name for net force, okay? Net force is another name for resultant. And so if you arrange these forces such that they act in the same direction, you will realize that calculating the net force for forces acting in the same direction is going to give you 7 Newton. But if you arrange these forces such that they act in opposite direction, then the net force is going to be the bigger force minus the smaller force, which is 1 Newton. But there's just no way you can arrange these forces, whether in the same direction or whether in opposite direction, such that they will cancel one another. Because for you to have a net force of zero, it means that the forces cancel one another. And therefore, these two forces cannot have a net force of zero. I hope that makes sense. If you have any other question, you can follow up with me during class. Same thing with this one. If you have two forces of 8 Newton and 12 Newton, again, you have to look at the two scenarios. You can either arrange these forces in the same direction, and if they are acting in the same direction, the net force is going to be 8 plus 20 Newton. But if they act in opposite direction, right, then it will be the smaller force that you will subtract from the bigger force, and the net force is going to be 20. So because the two scenarios give you both A and or B, then the right answer is going to be both of the above. Now this question is on the equilibrium law. Last time we were saying that when a body is at rest, it means that the net force acting on that body is zero. But it doesn't mean that forces are not acting on the body. It just simply means that the forces are being balanced, and that's what we call equilibrium. So what the equilibrium law says is the sum of all the forces that are acting on a body is zero. In other words, the net force acting on a acting on a body is zero. So when the equilibrium law applies for a body that is at rest, so if a body is not moving, automatically the net force acting on it is zero. But another scenario is that a body can be moving with uniform velocity, right? Or it can be moving but not accelerating. So if a body is not accelerating, right, that is also an equilibrium condition, right? So if it is moving in a uniform motion in a straight line, right, that is also equilibrium. And so both of the above is the right answer. So take note, when a body is not accelerating, right, it is not experiencing any net force. Okay? When you stand on two bathroom top scales with more weight on one scale than on the other, the readings on both scales will be, again, if you stand on two scales, right, whether you're leaning more on one than the other, the truth is that your weight will be distributed on both scales, such that at the end, if you check your weight on both scales, they will add up to be your total weight, right? This is the same kind of scenario. You have a weight, right, and you're suspending on a rope using your two hands, right, on both sides. So what happened is that each side of the rope is going to experience a tension force that is going to be half your weight, because you're hanging on two hands, your weight is going to be equally distributed on both ropes. And so your weight is going to be half. The tension that each rope is going to experience is going to be half your weight. All right. So that is that. That is that. And I hope you'll be able to write this down, catch up, and prepare for your test.